In this section, we will talk about the principles of electricity, or the basics that you should understand before dealing with electricity. We won't get into electrical safety yet. That will be covered in other parts that will come later. But it's important for you to understand the basics of electricity at the beginning so you can grasp the topic. So let's relate it to something we all know, the flow of water in pipes and hoses. The concept in electricity is similar to the flow of water which moves from certain places. Where the pressure is high, for example, if you have a fire pump, the pressure in it is high and it pushes the water so it reaches places where the pressure is lower. It's exactly the same idea. What makes electricity flow is the voltage difference. Not the pressure difference, but the voltage difference. So the voltage moves from places where the voltage is high to places where the voltage is low, and that's what makes electricity flow through the wires. It's the same idea. Water flows through pipes and electricity flows through wires. If, for example, in the pipes where the water is flowing, there happen to be sand, impurities, or any kind of obstacles, this would hinder the water from flowing through the pipes. It's the same idea with electricity. There's something called resistance, and areas with high resistance cause the current to flow less or with lower intensity. So it's the same concept. Now, the three main things you need to know about electricity are the terms. These are voltage, current, and resistance. Voltage is the potential difference, current is the flow, and resistance is the opposition. Voltage is represented by the symbol V, and its unit of measurement is the volt. As we mentioned, it expresses the pressure or force. It's the energy that makes electricity flow. Current, which is the flow, is represented by the symbol I and is measured in amperes. This represents the rate of flow of electricity or current in the wires. The last thing is resistance, which is represented by the symbol R and is measured in ohms. That's the omega, the Greek letter called omega, which is the unit for measuring resistance. As its name suggests, resistance opposes the current from flowing at the same intensity. So these are the three main terms. There are two types of circuits that we all know, series and parallel, or as we say, two types of connections, series connection and parallel connection. The diagram on the left is the parallel connection, and the diagram on the right, series connection. Parallel connection. As you can see, it looks like this. The power source, which in our case is the battery, of course, and the switch, and the current flows from here and reaches this point, where it splits into two parts. One part goes to the devices above. In our case, it's just a bulb, and the other part goes to the devices below, or the devices connected below. But in series connection, everything is connected one after the other. So how does this make a difference for us? Let's see. Let's look at the case of the connection. In the case of the devices above, like the bulb above or the bulb below, the voltage is equal. V1 equals V2. As for the current, it's the sum of the current flowing through the upper part and the lower part, because the current reaches here. And it splits into two parts. One part goes above and one part goes below. So the total current is the sum of the currents flowing in each of these directions. As for the resistance, you'll find that the resistance of this circuit is less than the resistance of each component individually. For example, if here it's 3 ohms and below it's 3 ohms, the resulting resistance is not their sum, but actually less than 3 ohms as well. That's how it works. This is for parallel connection, which is the parallel circuit. On the other hand, in series connection, the voltage equals the sum of the voltages of both components. The current is equal because it flows through the same circuit, so what enters here is the same as what enters there. It's the sum of these two. The more devices or resistors you add to the electrical circuit, the total resistance becomes the sum of all the resistances. In all of these various electrical setups, of course, within our modern homes, we consistently rely on the standard parallel circuit design. Because, for example, think about it, if a light bulb burns out at someone's house, that circuit is now broken because it's either the bulb or the switch at their place. The electricity has failed, so that particular circuit stops working, but at the same time, everything else that's connected in parallel is still working just fine. But in the case of series wiring, what happens if that bulb burns out? The entire circuit shuts down. In other words, if the wiring in houses was done in series and a bulb burned out in someone's house, the whole country would lose electricity. That's exactly the idea here. So that's the difference between series and parallel wiring. There are also other points to consider. Direct current or DC and alternating current, and the difference between them is simple. DC or direct current. The current flows in one direction, As we can see, the current I moves continuously in the same direction. On the other hand, alternating current flows in both directions. That means the current can flow from this side or from that side. Of course, in homes, the current is alternating, and that's why when you connect electricity, you can switch the wires around and the power will still work. And the device will keep working normally. There isn't a specific direction the current has to flow in because the current is alternating and moves in both directions. Alright, when it comes to the laws or equations you need to know about electricity, they're on the left side. The most important law is the relationship between voltage, amperage, and resistance, or the difference in potential, current, and resistance. V equals I times R, or if you want to calculate I, it will be V divided by R. So you can calculate any one of them if you know the other two, and if you hide one of them, as we'll see in the upcoming example, you can figure out the calculations for the other two from the signs. For example, if you hide V, you'll find that V equals I times R. If you hide R, then R will be the voltage V divided by the current I. In one specific form, the relationship exists, for example, between the electrical power P and likewise the current and the potential voltage difference, or alternatively with the resistance and the current flow. Also I, which is the current and its relationship with P, R, and V. So all these things together, P, V, I, and R. What is their relationship to each other and how are they calculated based on one another? You'll find that here. So you're supposed to have this equation memorized or remember it in case it doesn't appear in the exam. Because usually it doesn't show up. So you're expected to know this form by heart or have these equations memorized. Now, let's take a closer look at the specific example we talked about earlier. We have a standard DC electrical circuit here, which as you know means direct current. And right here is all of its relevant data for our analysis. The current is 0.5 ampere and the resistance is 5 ohms. And I'm being asked to calculate the voltage difference. So as we said, to calculate the voltage difference, I'll hide that upper part. So I'll get the equation I times R. I'll multiply these two numbers together and the voltage will come out to 2.5. It's a very simple calculation. You don't even need a calculator for it. It's easy. The second thing is, how do I calculate the voltage in an alternative circuit? I also have an example. I have a circuit with 500 watts. The resistance is 3 ohms and the angle of lag is 25 degrees. Here now, things will start to involve a bit of calculation. The equation we'll use is V equals P over I, or power over current divided by cosine theta. What does each of these terms mean? Let's start with V, which is the voltage. The I is the impedance, and that's another word. Impedance is another term for resistor or resistance. Both serve the same function. Its unit is the ohm. Theta is called the phase angle, and this is found in alternating current. And the last thing is power, measured in watts. P stands for power in watts. Now that we understand what these symbols mean, you can just take the numbers from this question and plug them in. For example, P is 5,000 watts. I, the impedance, is 3 ohms. And the cosine theta, which is cosine 25. And all of that will be under the square root. On the calculator, you can calculate the part inside, as we'll see now, and then take the square root to get the number. So let's see how to do this on the calculator. Okay, so how do we solve this problem using the calculator? Of course, everyone will do it differently depending on their experience with using the calculator, and then they'll take the square root after finishing the calculations. Or from the very beginning, they can keep in mind that it's a square root and use parentheses in the calculation. So let's look at both methods. You can use whichever way is more comfortable for you. The first method is to take everything that's written in the equation, including the square root and all its components, and calculate it all at once. And the second method is to calculate what's under the square root separately and then take the square root of that. We'll see now, and to understand the topic, the square root. Under the square root, there was a numerator and a denominator. So what are we going to do? We'll take this bracket to calculate the 5,000 times 3, which are the things that were in the numerator, over what's in the denominator. What was in the denominator? It was cosine 25. So we'll write cosine 25. And close the bracket. Enter. So I got 128.46, and when you round the number, it becomes 129V. As we saw in the question, this is the first method because you from the beginning wrote what's under the square root. The second method is that we calculate 5,000 times 3. This gives us 15,000 right away. After that, we'll divide it by cosine 25. We agreed that the bracket isn't important, so the number will come out normally, and then you take the square root at the end, the square root of the answer. You'll get the same result, 128.64. Which method is easier for you? It's up to you if you don't prefer it. If you use a lot of brackets and it confuses you, you can divide everything separately or calculate each part on its own and then add them together, but still, so it's up to you. Practice both methods, see which one suits you best, and use it. The three components that make up the electrical circuit, which are the resistor, the capacitor, and the inductor. So what's the difference between them? Even their shapes, if you look at them, are just like what you'd see if you opened up any old game, for example. You'll find these components inside. So what's the difference between them? The first one, all the way to the right, is the resistor. You see this a lot in games. And of course, it's measured in ohms. The capacitor is the one. In this form, it's measured in farads. And the last one is the inductor. The inductor basically means a device for induction. It creates induction from the word induction. It's measured in henries or H. So what's the difference in function between each of them? The resistor, as we explained before, resists the current flowing through the wires. As for the capacitor and the inductor, they both store energy. The capacitor stores it in the electric field. And one of the functions of the inductor is that it converts electrical energy into a magnetic field. So these are the differences between them in a nutshell. The resistor resists the current flowing, the capacitor stores energy in the electric field, and the inductor stores energy in the magnetic field. So these are the differences between them. Now let's take a look at this question. Calculating resistance in DC circuits, meaning we will calculate resistance in direct current circuits. So the question says, and it gives you a symbol that we're supposed to not know, which is equal to 5.6 times 10 to the power of negative 8 ohm meters. Now this specific number, expressed in ohms, represents the resistivity. Consider a cylinder with a length of 4 centimeters. All right, let us proceed. To fully understand this question, whenever you take any standard light bulb and look closely inside it, you will find a very small thin filament exactly like this one. Could you please provide a detailed explanation regarding the specific identity of this particular location, including its name, its geographical significance, and any other relevant historical information that defines what this place actually is, which we still don't know what it is? The resistance R we have is for the one with a certain length, and we're required to calculate it, the area. So how do we do that? This is the equation we're going to use. R equals RHO times L over A. I want to calculate the A at the bottom here. So I'll rearrange this equation to isolate A on its own. So when I rearrange it, it will look like this. Okay, so what is R? Of course, it's the resistance of the circuit, and we've already learned that it's the resistance present in the circuit. Rho, which is the resistivity of the metal. This resistance isn't a fixed value for all materials. So depending on the material, there's a specific resistivity coefficient or resistance for that material. In the case of tungsten, they've given you its value, as we saw in the question. L, of course, is the length, and A is the cross-sectional area in square meters. So if it's in the shape of a cylinder, just like they gave us in the question, they gave us the length of this cylinder. And what I'm required to do is calculate its area. How do I do that? Here's the equation that calculates this. So after rearranging the equation, I'll leave the A by itself. And I'll take these numbers, which are 5.6 times 10 to the power of minus 8 multiplied by 4. Here they've given it to me in centimeters. And this is one of the things you really need to pay close attention to in the exam. You need to know the unit for each of these symbols. So we said that the unit should be in meters, but here it's given to you in centimeters. That's why he multiplied the 4 by 10 to the power of minus 2 to convert those 4 centimeters to meters and then divided by the resistance, which is the ohm. After that, just use the calculator. The calculator will multiply all these numbers together and give you the area. So let's also see how to enter this into the calculator. This question is easy because it's just direct substitution and there aren't any different operations like addition, subtraction, parentheses, or things like that. No, it's just multiplication and division. And with multiplication and division, the order doesn't matter. Both operations can be done together normally. So we multiply 5.6 by 10 to the power of negative 8 by 10. And the power is this symbol, so it gave you the form shown above, which means it will write its exponent. And we agreed that there's a difference between subtraction and the negative sign. So I'll make it negative 8. And it's important that I don't keep writing. If I keep writing everything after that, it will come right next to the exponent. And I don't want that. I want to move out using the arrows like this. And then perform the multiplication operation by the value of 4 multiplied by 10 raised to the power of negative 2. And then even without that factor, I will still definitely need to relocate my entire operation out to this specific location. And without using parentheses, I will perform a division calculation by the decimal 0.35. So the resulting number I get has a very large sequence of zeros like this, and then finally at the very end. If the question in the exam doesn't give you this number, and most likely it won't, it will come in the scientific notation format, like we saw in the question 6.4 times 10 to the power of negative 9. How do I get to this number? As we learned at the beginning, by using the calculator. The calculator is currently set to normal mode. So if I go down with the arrows to normal and change it to scientific, then press enter, I'll exit, do quit, and perform the calculation again. That is, press enter again, so the result will appear in a different format, which is the scientific notation. 6.4 times 10 to the power of minus 9. And that's exactly the number we got in the calculations and the one you'll find among the choices. Okay, if I want to go back to the standard format, I'll use the arrows to select normal, then quit, then enter, and it will display again in the standard format. So that's the difference between the two formats and how to easily switch between them. The next part is about calculating resistance in a series circuit, which is also an easy part. And the question says, calculate the total resistance. You have 3 resistors in a series. That means I have 3 resistors, one after the other, in a series, meaning connected in series respectively. 2, 4, and 6 ohms. So what is their total resistance? As we said before, the difference between resistance in series and parallel circuits. We explained this before. So it would be the sum of all of these. So you add these numbers together and the total resistance will be 12 ohms. Of course, there's no need for us to do it depending on the topic. It's simple, really. Now, the resistance in the parallel connection. Regarding parallel connection, it is the same question we were just discussing in our previous conversation, but we'll rearrange it. It won't be in series, it will be in parallel. And the numbers are the same numbers, which are 2, 4, and 6. So what will it be? I want you to notice. Notice here that the smallest one among them is 2 ohms. So let's see. When we calculate all 3 together, what will the total resistance of the circuit be? This is the equation we'll use. 1 over R in parallel, which is the total. It will be equal to 1 over R, 1 plus 1 over R, 2 plus 1 over R3, and so on. So you divide all of these by each other. It will be a half plus a quarter plus 1 over 6. When you add up all these numbers, 1 over R parallel will be 0.92. When you take its reciprocal to calculate R, this parallel will come out to be 1.9 out of 100. Why am I telling you to remember the smallest one? Because as we said in the explanation at the beginning, the total resistance of a circuit with parallel connection will be less than the smallest one. And that's exactly what we got. The total resistance turned out to be 1.9 out of 100, which is less than the smallest one. This is another way as well, so you can know, even during the exam, how to double check the numbers. Did you make a mistake in the calculations? Or if you have 4 choices in front of you, you should eliminate certain options based on your understanding. So even if your calculations turn out wrong, if you understand correctly, you'll redo the calculations and not just pick the number that comes out. So this is also one of the things or tricks you need to pay attention to in the exam. Next, we'll take an example of calculating capacitance in a series circuit. That is, connected one after the other in series. I have 3 capacitors with individual values 0.1, 0.2, and 0.3. Microfarads series means one after the other. What is the total capacitance? This calculation is similar to the calculation for resistance in parallel circuits. So also 1 over C for series equals 1 over C for each one of them, or the sum of 1 over C for each one. So when you divide each one like this and add them together, you'll get 1 over C, which is 18 and 33. And when you calculate the total capacitance for the whole series, it will come out to 0.55 out of 1000. Now, what if the circuit is parallel? That means these capacitors are connected in parallel, so let's use the same numbers and calculate it. In this case, it's just a straightforward addition. You add them together and it comes out to 0.6. As we said, the three components of an electrical circuit are resistors, capacitors, and inductors. We've already calculated the resistors and the capacitors, so now we'll also calculate the inductors. Here, we're talking about inductance in series circuits. The information given in the question says that there are 3 inductors connected in series, meaning one after the other in a sequence. And these are their values, 35, 0.4, and 0.5 microhenries. So what is the total inductance in the series? Now, in circuits, the calculations here are the opposite of the calculations we did for capacitors, where we used 1 over C. But here, in the case of series connection for inductors, we add them together, so the result will be 1.25. And you'll find in this question that when calculating the inductance in a parallel circuit, the calculations are similar to those for capacitors in a series circuit. The topic might seem a bit confusing, but when you sit down, break it apart, and put things side by side, you'll find everything becomes clear. All of this helps you during the exam so you can answer without getting mixed up, or at least know whether you should add the numbers directly or add the reciprocals of those numbers. That is, 1 over each number, then add them together at the end. You will likely find that these complex concepts become much clearer and easier to understand, especially when we are dealing with the specific behavior of inductance in parallel circuits. And here, in this particular question that I have presented on the screen, I haven't provided the final answer for you. Instead, I am going to need you to take the time to work through the calculations and find it for yourself to ensure you have mastered the material. You'll find that I've left the solution to this question below the video, so what you need to do is pause the video, do the calculations, and then check to make sure you actually got the correct answer or not. How does electric shock happen? An electric shock occurs when current passes through the body. The severity of the shock varies depending on many factors, like age, the path the current takes, that is, how it entered and exited the body, and the nature of the body itself. Was the person wet or dry at the time? Male or female? Old or young? The health condition depends on many things. So electric shock happens when current passes through the body, entering from one place and exiting from another, and the intensity also depends on the duration. That is, how long it stayed in the body. These can, God forbid, cause death. So how do we know the details? The details of electric shock and its effects can be found here. In this table, the table starts from less than 1 milliampere, which people usually won't feel at all. At 1 milliampere, you'll start to feel the current a little, and then it gradually increases until you reach numbers like 10,000 milliamperes. Problems with heartbeats and death may become certain at that point. So for this table, you should generally be aware of the effects of electricity, as you might be asked about something like this in the exam. The last thing we'll talk about is how to control electrical hazards. Generally, the danger of electricity comes from one of 3 things. The equipment itself has a problem, it was installed incorrectly, or it is unsafe. The second thing is the environment in which the person is working. It could be a wet environment, like standing in water or something similar. This can increase the risk of electrical accidents. And the last thing is unsafe work practices. Unsafe practices. Each of these factors can contribute to increasing the risk of electrical accidents. We will talk about the topic of electricity and static electricity later when we talk about things like fire protection and static electricity and their relationship to each other. So we will discuss these in more detail, like arc flash and such topics. We'll cover them in greater detail. But the purpose of this lesson is for you to understand the basics of electricity before we get into those details.